For activity 3, we're going to look at this car moving on a vertical circle, which is another classic example, so I will follow the activity exactly. So we know on this frictionless surface or frictionless stress, there's not going to be any acceleration because the car is just going to move forward without any friction. There is, of course, a gravity going down, but it will be cancelled by a normal force. However, as the car goes up, it should slow down, so we know the acceleration or the total force should point backward, and they will have non-zero acceleration, so we know as the car moves up the circle, the net force will grow bigger as it moves upward. We can try to get quantitative by first drawing the force diagram. Now let's draw the gravity, which is pointing downward. It's always downward because that's what gravity does. And for the normal force, we know it will be pointing in a direction that is normal to the surface. And now the surface is a tangent line to the circle, so the normal force will point toward this direction. So this is how we have our forces, and we can break them into the components. And in this case, I'm going to break it into the component that is perpendicular to the surface and tangent to it, because we want to solve later the speed of the car, which is just the tangent component of velocity. So I want to break the gravity into a component that is tangent to the track, which is this one, and the component that is perpendicular to the track. So here I break the gravity into these two components. So we want to solve for the speed in terms of angle theta, and we can have our force diagram here telling us that because the acceleration will just be the one that is tangent to the track, so what we want is just this component. We know that this angle is theta, which tells us that this angle is also theta. So this component will be the gravity times sine theta, and then the component perpendicular to the track should be cancelled by the normal force. So we know that this should equal to the gravity, and the component need to be in sine theta. And because we know the gravity will slow down the speed, so there's a minus sign. And to turn the force into acceleration, we divide it by mass, and then we get that the acceleration tangent to the track, which will give us the derivative of speed, will be minus g times sine theta. Now we can do some trick to get the theta and v out of it. Here we already have dv dt equals dv d theta times omega. We can further use omega equals speed divided by the radius of motion for a circular motion, and write everything in terms of v. But in this case, because the car has a initial height, which is h1, so we know that the circle that the center of the car is drawing is not actually having a radius of capital R, but the one that is capital R minus h1. So in this case, we'll have capital R minus h1 under v. So we write dv dt in terms of dv d theta omega, which omega can be written as v divided by r minus h1, and this is g sine theta. We then move everything that is v here, which is just v dv, and then let's move everything that is theta to the other side. So now we have everything that is theta on the right hand side and v on the left hand side. And we can now integrate it from v equals v1 to v2 and sine theta from angle 0 to whatever degree that is. So I'm going to add a prime here to separate the integration parameter. So the left hand side will give me 1/2 v2 squared minus v1 squared. The right hand side will give me just the cosine of theta minus 1, because sine minus integral will give me cosine, and cosine theta when theta equals 0 is 1. So this is how I get this cosine minus 1. Now I can try to find the h1 and h2 from this cosine value. When we have our track here and the car is at somewhere here with the height h2, and the h2 is the height of the center of the car to the ground. We see that if we have our r here, then from the center of the car, the distance here to here is actually just r minus h1, and this distance will just be r minus h1 times the cosine of theta. So this is when, and the entire distance from the center of the circle to the ground is r. So we find that the height h2 is just r minus h1 times cosine theta. So we can see that we can get this expression from this parenthesis. Expand this stuff, give me r cosine minus r minus h1 cosine plus h1. And you can expand the thing on top here and see that it is indeed a combination that gives me h2. So we see that this is just h1 over here, and all the other stuff is the combination of h2. So here I get that the change of velocity square is related to the change of height directly.